This video, we're going to prove a very important theorem. If the order of G is p squared, where p is a prime, then G must be abelian. If you like watching mathematical proofs like the one I'm about to give, please subscribe to my channel. That's what we do on the channel. We prove mathematical theorems. Okay. So what we're going to do is we're going to look at the center of the group. Note that the order, well, let's not talk about the order yet. Note that the center of G is normal in G. In particular, it's a subgroup. Hence, the order of G, this is by Lagrange's theorem, the order of the center of the G must divide the order of G, which is p squared. So the order of Z of G, the center of G, is contained in the set 1, p squared. These being the only factors of p squared. Okay. Now, from the previous video, since G is a p group, the size of G is the power of a prime. We know that the center of Z, is non-trivial. We know that the center of G is non-trivial. That is, it's not E. That is, the center of G is not just the element E. For the record, the entry fee to get into Z, or the center, is to commute with every element of G. And E clearly commutes with every element of G. E is always in the center of G. But since Z is not just their singleton E, this implies that Z of G is greater than, but not equal to, is bigger than 1. Well, this then implies that the length or the order of G can't be 1. That implies that the order of G is p or p squared. Now, if it's not p, then the order of the center must be p squared, which is the order of the group. That would, if the order of the center was p squared, that means every element of G is in here. And again, to get in here, you must commute with every element of G. So if the center of G, if the order of the center of G is p squared, that means every element in G commutes with every element in G. Oh, that makes G abelian. So I want to either show that if the center of G is equal to p, then G is abelian, or that the center of G cannot equal p. We're going to prove the latter. Okay. So suppose that the order of the center of G is p. Well, this is not all of G. G has p squared elements. So choose some x not equal to E in G such that x is not in the center. Now we consider the center of X, which is the set of all G in G such that G commutes with X. Only some G's commute with X. Maybe all of them. Clearly, C of X is not empty because, for example, EX equals XE and X itself is in there because X times X is, if I switch them, well, it's X times X, which is true. Okay, now I claim that the center of G is contained in C of X. Well, this is clear since every element in G commutes with elements of every element in the center of G commutes with elements of G. Since X is in G, every element in Z of G commutes with X, and I have a typo, Z of G. Okay. So what we have now is that the order of the centralizer of X is at least P plus 1 elements. Every element of G, well, that's P, and we found an element that was in their centralizer of X, but wasn't in Z of G. Okay. Note that C of X is a subgroup of G. This implies that C of X, the order of C of X, must divide the order of G, which is P squared. Well, since the order of C of X is bigger than P, and C of X must divide P squared, that implies that the order of C of X is P squared. But now that's the order of G. That is, C of X commutes with every element in G. Well, I should say X commutes with every element of G. This implies that X commutes with every element of G. That is exactly the entry fee for X to be in the center. But we chose X not to be in the center. So this is a contradiction. That is, the center of G equaling P cannot be true. Okay. Well, if the center of G, let's see, if it can't be 1, and it can't be p, then it must be p squared. This means that the center of z of g is p squared, which is the order of g. That means that every element in G commutes with every element in G. All p squared elements of G are in the center. Okay, so every element of G is in the center. And how did they get in the center? Well, they commute with every element of G. So what we have is every element of G commutes with every element of G. Hence, Z of G, well, hence G is abelian. Because every element of G commutes with every element of G. That's exactly the definition for G to be abelian, and that completes the proof. If you like watching mathematical proofs like this, seriously consider subscribing to my channel, as that's all we do here. As always, tell your friends, family, and enemies to subscribe to my channel. Please post a comment, click the like button, subscribe to my channel. See you guys in the next video. Watch and learn.